Welcome back to the lab. Guys, I blew up the inverter. Okay, what happened? Two things. First, I was working a little bit ahead on the project, getting things ready for the next couple videos, as one does, and I was setting up the last test, and it was working great. We had sinusoidal voltage regulation. We had it stepped up to 220 volts AC. We were almost done. Time for the line and load regulation testing. Time for the efficiency calculations. In my excitement, I began using the 110, 120, and 100 volt taps of our auto transformer, and I was using that to switch between the different input voltages to try to dial in the output that last little bit without actually changing the code to regulate to a new voltage set point. But it was looking great. No perceptible noise or ripple, voltage regulation. It was sinusoidal, 60 hertz. What more could we want? Oh, I know what we could want. 240 volts, of course, so I swapped around the auto transformer winding to the setting that would make it double the mains voltage, and then there was a small pop. Pop doesn't really describe it well. It was more like the sound of stepping on a small twig, that ominous snapping noise. One decisive crackle, and it was all over. The two outputs now appear to be shorted from one to the other, even after replacing the FETs. The waveforms just don't look right anymore, and the FETs are behaving like they're either shooting through or loaded in the no-load condition, both of which are terrible. Either way, we've damaged the FET drivers, the output filter, maybe both, but something isn't happy. So, what happened? What made that crackle and make this all blow up? Dielectric breakdown. Stupid thing. So what we were doing is using a transformer backwards. It's rated for 24 volts on the output and either 120 or 240 on the input. And so we just drove the low voltage winding to step up our voltage. And we were driving this with a 12 volt sinusoid, so I used the 240 tap so we'd get 120 volts in the output of the transformer with a 12 volt input. I mean, it's nothing really special. This transformer, it's just 100 volt amps. I think it was only 70, and that was enough at the time. All we wanted to verify is that we had voltage regulation, and we wanted to get an efficiency measurement. If anything, this would have been a worst case because we would have had losses from both the step up and the auto transformer, not to mention all the switching losses and whatnot that come along with the PCB. And in theory, there's nothing wrong with this configuration, even though we're driving a transformer backwards and our DC bus voltage is 40 volts. However, either due to marginal stability in my control loop, some resonance between the output filter and that step-up transformer, or the inductive load step down the line when I switched the auto transformer back in, something, somewhere, exceeded the rated voltage of the primary winding, the 24 volt one, by applying enough voltage to cause this transformer winding to arc over and weld itself together, effectively shorting out the MOSFETs as if they were experiencing shoot-through. Since we didn't implement the current limit, rather any current limit in software yet, the micro just kept driving the inverter as if nothing had gone wrong, and we cooked the crap out of our GAN FETs as well as the transformer. So that wasn't ideal. This is pretty disappointing. Especially disappointing since we only have one of these boards, and it'll be impossible to determine if we fixed all the issues before moving on to the next iteration of the design without one. Then again, one doesn't learn very much by things going smoothly. Could have been worse. At least I have a few most probable causes for the failures, and we can try to mitigate all of those potential causes of failure when we go on to the next board spin. That way, when we perform our short circuit test on the final inverter output, it should cut out as we expect to save itself, you, the load, whatever caused the short circuit. Now, while I was too busy playing with circuits to turn on the camera before I blew this up, I did take some pictures and recorded immediately after I blew it up just to try to capture my reaction to the whole ordeal. Let's check that out. There's been a minor setback in Project Darwin. And, well, I blew up our FETs. Rather, this transformer blew up our FETs. So, why did this transformer blow up our FETs? Well, it's rated for 24 volts. That's great, and I was using it in the 24 volt configuration, and I was using it to step up the AC up to 120 volts. And I added an inductive load step to it, and either the control system freaked out or something else happened. It happened very quickly, but all of a sudden there was just this little crackle noise, and I was like, well, what the heck is that? And unfortunately I didn't have the camera rolling because I was like, oh, I'm just going to test it real quick, and I wanted to step it up and hook in a light bulb and see if it exploded or if it worked. But the problem is that load spike overvolted our secondary side winding. It couldn't have gone above 40 volts. Like, that's our DC bus voltage. It would have been clamped if it went above our DC bus voltage. Actually, I should add clamping diodes to limit it to the DC bus voltage, because that should be higher than anything we see on the output, and then we'll know that our transformer can be rated for it. We should blow up those diodes before we blow up a transformer. These things are not cheap. Well, rather, this one was cheap, but in our final design, that'll be a 1500 or 2000, 2500 VA transformer. And those cost like $300, and I don't really want to overvolt them and short them out. So that was a good idea. I should add some clamping diodes, but I didn't for this, and it shorted out the secondary side winding, which shorted out the inverter output stage. And since somebody was lazy, was efficient, and didn't implement the cycle by cycle current limit, where it would have like tripped and then did a soft start. The soft start code needs to get written. I didn't write it because it didn't matter until right now, but we blew up the FETs. And well, if you've been watching the series, you know those are GAN FETs, and those FETs are pretty expensive. Thankfully, I keep a pretty good stock of components here in the EEforEveryone lab, and I'm pretty sure that I've got some NMOS FETs on the shelf here somewhere. I think they might be in here. Weird. There's only a couple more places these could be. Like, I reorganized everything not too long ago. PNP train. I've got some power NMOS FETs. Here they are. Stupid thing. Alright, so I've got some NMOS FETs. Here, now watch. In post, I'll like circle it and zoom in, so when I'm running around like an idiot, it'll look obvious. Yeah, got some extra NMOS FETs here. These are not GAN FETs. They're simply not GAN FETs. And in fact, I did not get them from a reliable source, and for all I know, it could be a mix of NFETs and PFETs. And you know what? That's not great. And in fact, I've observed some of these FETs not behaving as one would expect. Pretty sure that some of them are actually PFETs. Sorry about the bag noise. But we'll just test them all on the bench here. They're IRF Z48Ns, and I'm just gonna head over to the computer, see if these happen to meet our specs, and if they do, I think we'll just throw them in the design. And we'll see if they still work, and I have a feeling that if we blew up the FETs, this will not be the first nor the last time. And I still have got an inverter stage to test, so yeah, we're just gonna have to press forward. And we know that the GAN FETs worked, and we know that they were fine, but since we're bringing our DC bus voltage down, since we're going to need a transformer, the reason why we need a transformer in the first place, the reason why we even got this darn thing is because I want to keep the output of the supply looking as if it were mains. And what that means is that I need to short neutral to ground as if it were tied back in the distribution panel. And that's not normally something that you would do, but some equipment might demand that those two are the same potential, otherwise they'd have leakage currents in places they weren't designed for, and that could really screw some stuff up. And I just don't want to take that risk. So by shorting the two together, that'll mean that it'll look like a voltage source from ground to line and approximately 0 volts between neutral and ground. And that'll look exactly as if you'd plugged it into the wall. So that's why we're doing it. And as long as we're trying to duplicate that in case there's a piece of equipment plugged in that relies on that dependency, I would hate to blow something up or zap someone or have the case of a piece of electronics be tied to neutral, which is actually like floating around at like 50 volts AC with respect to ground. Like, it just doesn't sit right with me. So I'm going to make neutral tied to ground the way it was meant to be. And that's what the transformer let us do, while also reducing our DC bus voltage, which will make the conversion from battery voltage to our DC bus easier. And it'll mean that we can have a step down PFC from mains. And, that all. It's fairly vanilla, and I don't suspect we'll have any issues with that topology. If I had a higher bus voltage, I'd be tempted just to regulate mains, and that wouldn't be very efficient. But so, if you didn't catch that, this video we're going to fix the fact that the inverter is blown up and get it working again. So, RIP inverter stage. But basically what we're trying to do is we're trying to take this inverter and figure out exactly how broken it is. I measured a short on the output, and then I removed... whatever, it doesn't matter. It's too traumatic. Can't relive it. But what I don't know is how far back that propagated. So one, I'm just gonna take all these leads off of the output. They're not doing anything. And I want to re-cable manage this when we put it back together anyway, because the cable clutter was triggering me in a way that words cannot describe. What I'm going to do is I'm going to trace this back to the gate drive signals and see just how bad, and or broken it is. So PWM-A input. B input. Turn off the math channel here. Alright. You can see our PWM, and it's doing its thing. Looks great. It's this nut right here. That does not look promising. Let's make sure we are triggering correctly. Why are we not triggering anymore? Triggering it over here. Lots and lots trigger. Let's try this one. Oh? What's going on here? Hey! Might have just been a scaling issue. Okay. So here's one PWM signal coming across. Hey, there's another PWM signal coming across. There they are. Okay, so the gate drive IC... Ooh, wait a minute. This one doesn't look right. Let's flip PWM A and B. And then we should see it flip sides. So now, over here, we see some craziness there. Yeah, looks like this gate drive IC is blown. So what happened is when we hooked up the same input to the other gate drive IC, it was, for lack of a better word, hashtag fine. It is definitely not fine. Let's just make sure the boost circuit's working. No, not even a little bit. So even the boost circuit completely malfunctioning around this other chip. You can see it's actually able to drive the chip and it's generating its higher voltage. Drive the gate width. It's actually switching. Alright. So looks like we fried a gate drive IC and the FETs themselves. I'm going to swap out these FETs, this gate drive IC, and then we'll give her another go. Where do we go from here? Let's talk about our plan B. We'll discuss a few things that I've learned during the project and walk through the changes that we'll pull into our updated system architecture. This is all leading into what is hopefully our final prototype inverter. That's right, we need to kick off our production-ready board because, well, we don't have any other boards to work with anymore. I've learned a lot about do's, don'ts, and probably shouldn'ts with regards to inverters and UPSs. May as well go for the gusto, am I right? For now, I'm just letting you know that because I got too excited to pull out the camera while I was working, some apprentice connected this inductive load through the step-up transformer, the primary side of the transformer being driven by the inverter, welded itself together. I'm having flashbacks. We're going to need to wait a little while longer to get to the content that I had planned done. That said, we're going to learn from my mistakes. We are going to walk through making a DC regulator and an AC inverter using the filtered H-bridge topology. We are going to get the output voltage of our inverter up to 120 volts AC. You know, after we clean up this mess, re-architect the thing, design a new board, have it manufactured in China somewhere, it might take a little while, but we'll get there. Blowing up a board is not enough to stop this project. Blowing up 2 boards though? I mean, yeah, I could do it. Good thing we only made 1. The proof of concept phase of Project Darwin came to a swift and unplanned end. Even if I didn't get to share some of our awesome testing with you so you could see how excited I get when I see a sine wave on an oscilloscope, we still made it a fair way through the proof of concept phase before the thing exploded. Subscribe to be notified for our future videos where we'll cover some of those intermediates like closed loop control and how to design high power circuits. I think that destroying hardware is awful, but our UPS will be great. If you think so too, let me know by hitting the like button on this video, getting subscribed to the channel, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EEforEveryone, and thank you for staying till the end. Bye!